In terms of raw computational power, the cellular telephone that most of our planet's population carry with them wherever they go would have been considered by most a supercomputer only 30 years ago. What applications must do to meet user expectations is driving new development methodologies, infrastructure architectures, and delivery practices. Change is not just coming, it's here, and if you're not rapidly adapting to the change, you won't be able to compete. But why change? IT has been in the midst of a significant change in the way it operates over the last decade, indicated by the emergence of the three industry trends: agile development methodologies, cloud resources, DevOps delivery practices. Some of this change is simply evolutionary, improvements initiated out of the necessity to continue advancing the way hardware and software are used, developed, and delivered. Some of this change is opportunistic, improvements initiated by visionaries who see a new way to meet the needs of a market. But the most significant driver of these changes is the geometric expansion of people, devices, access, data, and the software used by each of these. With the passing of time, user expectations and needs changed, along with the environments in which applications live. This drove further changes in the expectations and once again to the application environments. This dynamic cycle challenged software developers and architects to keep up with the impacts these changes had on the applications we build. There was a time when batch and time-shared systems, such as mainframes and minis, ran applications for a small set of users with text-based user interfaces accessible from a few physically connected terminals. During this era, these systems tended to be physically large, and although they could have external storage or user interface systems, they tended to be treated as a single system. Applications were monolithic, and the resource requirements for an application didn't change greatly from one execution to the other. So, there was little need for the application or system environment to expand or contract the resources available to an application. The subsequent PC era provided a low-cost way for users to have their own computing resources. Applications were developed to meet individual user needs, but applications shared by multiple users were still largely delivered using mainframes and minis. The introduction of networks of PCs required a new architecture to support applications shared by multiple users. This drove the development of the client-server software architecture. Applications could support multiple users, sharing data between them. Supporting multiple users required that systems could be expanded as demand for application access increased. However, since these applications were typically accessible to only a controlled set of users, resource demands and changes could also be controlled. Changes to address this increased need for resources were handled as upgrade and maintenance projects, often with months or years of advanced planning. The introduction of web-based applications has dramatically increased the expectations of users. Users now expect applications to be available all the time from any of their computing devices, without downtime and without limitation. They expect to receive new features and corrections in a matter of days or weeks, not in months or years. It is simply not possible to control the number of users of a web-based application, or to plan and schedule upgrade and maintenance projects. Applications must expand to react to increased user activity and then contract when user activity decreases, and both must occur immediately and automatically when the activity is happening. Legacy deployment, testing, and development practices are not flexible enough to accommodate these changing user expectations. Application architecture has evolved in response to changing user access requirements. The earliest architecture was single-tiered, running entirely within one system. This has been used for generations with mainframes, time-shared systems, and PCs. The two-tiered application typically contains a server running background services and a client that provides a front-end interface. A commonly used example of a server is a database management system. This often runs in the background providing services for multiple applications that can then provide user interfaces for help desk, sales, order entry, and many other online transaction processing applications. Multi-tiered applications extend two-tier architecture by continuing to add more services to the backend. Web-based or cloud-native applications are extremely modular, scalable, and resilient. Frequently, this includes a web server, a DBMS, a load balancer, a cluster manager, and other services that are required to enable highly scalable and resilient web-facing applications. The architectures employed by these types of applications go beyond multi-tiered. Accommodating these app architectures has significant impact on the process by which applications are developed, tested, and deployed. Legacy development testing and deployment practices struggle with the dynamic and complex requirements of these cloud-native app architectures. Another challenge facing IT is the unreliability and unpredictability of its development methodology. Typical project management techniques, when applied to software development, have failed. The waterfall methodology fails because it expects a complete understanding of the problem in all the systems the software will interact with, as well as well-defined and unchanging requirements. Applied to software projects, this methodology has historically resulted in late, over-budget projects that fail to meet user needs. It fails because it is almost impossible to meet all of the initial conditions. When any of these conditions cannot be achieved, there is significant risk of failure to meet schedule and functionality expectations because it is difficult to accommodate new or changing requirements, and it is difficult to address issues found late in development. Furthermore, because the working product is not available until the very end, functionality and integration issues are often not discovered until it is too late to correct them. And for the types of complex, scalable, evolutionary software being developed, this methodology often creates more problems than it solves. A collection of lightweight software development methods evolved in the mid-1990s in reaction to the perceived heavyweight waterfall-oriented methods, which critics called heavily regulated, regimented, and micromanaged. In February 2001, 17 software developers published the Manifesto for Agile Software Development. In this manifesto, the authors state a set of values for software development. They identify a set of principles to accompany these values. Several methodologies have emerged to replace waterfall in a desire to achieve these agile values and principles. In 2013, Capers-Jones evaluated the prevailing software development methodologies across a variety of factors to identify their effectiveness. He concluded his evaluation stating, "The phrase, 'Be careful of what you wish for, because you might just get it,' seems to be appropriate for these methodology comparisons. Methods such as Agile that focus on speed are very quick. Methods such as TSP, RUP, and CMMI-5 that focus on quality have very few defects." In the end, it's clear that these agile methodologies are being adopted and are improving the results, but are they also creating further challenges within IT? These agile methodologies are effective at improving time to delivery, feature functionality, and quality. However, since these methodologies tend to be iterative, value quick delivery of working software for user review and testing, and implemented within the development organization, they often hit a bottleneck when moving from the developer to the test or production teams. Code starts to stack up waiting for internal testing, then waiting to be deployed into user testing, and finally waiting to be deployed into production. These deployment delays prevent the type of agility needed for effective business on the internet. These development delays are traced to two issues. silos of people, and silos of infrastructure. Instead of working together, teams involved in software definition, development, testing, and delivery sometimes perceive their colleagues as combatants rather than collaborators. The teams within each of these disciplines have their own set of objectives and practices, and often these are at odds with those of their colleagues. Deliverables get tossed over a metaphorical wall with little thought of what impact the work of one team has on the work of the next. These culture clashes create significant obstacles to agile business performance. Furthermore, infrastructure resources are often siloed as a result of applications that expect to be the only user of a set of compute, network, or storage systems. This happens when developers, testers, and production teams each have their own set of resources. In the former case, the silos are a challenge because they do not permit high utilization required for adaptive, scalable applications. In the later case, the silos create chaos during installation when applications that work in development don't work in testing, user, or production environments. Virtualization is breaking down the infrastructure silos between compute, network, and storage, but the silos often still exist between development, testing, and operations. This presents another challenge, ensuring that development, test, and production environments are configured identically. Differences between the environments used by these separate teams frequently slows the reliable delivery of software and often results in a blame game. Instead of working together to overcome failures in testing or development, teams focus on assigning fault for their issues. Those who have overcome these challenges are excelling. Software is at the heart of these businesses. Their success is tied to their ability to rapidly adapt to the changing nature of their business and their customers, and this requires them to be able to rapidly update the software that drives their business. Within all the challenges ahead, it's clear that changing these outdated methodologies, infrastructures, and cultures is a critical factor in the success of online businesses. Adoption of these development methodology changes has gained momentum from over a decade of acceptance. Adoption of cloud and virtualization changes have accelerated for nearly as long. The DevOps movement may be a bit more of a recent change, but its adoption has been rapidly gaining speed. The DevOps principles, practices, and tools are the focus of this course. Are you ready for change? Good.